Hi, this is Kurt Laniker. I'll be talking this week about an emerging technology that has fascinated me for years, and that is the concept of harnessing the power of nuclear fusion to help solve our world's energy crisis. Now, most people have some familiarity with nuclear power, at least in its application to atomic weapons and the power plants that we get some, but not much, of our current energy from. Fewer people, however, understand that there are two very different types of nuclear reactions, with very different consequences, and that as of today we are only able to harness usable energy out of one of those reactions. In this presentation, I will briefly describe the history of nuclear power, the difference between nuclear fission and fusion, and the potential world-altering possibilities available with the advent of fusion reactors. Nuclear fission was first developed during World War II as a weapons research project. It culminated in the detonation of atomic bombs over Hiroshima and Nagasaki in 1945. After the war, scientists began conducting further research for practical applications, and were able to develop nuclear reactors that could produce electrical power by the early 1970s. These reactors are still in use today and account for approximately 5% of the power that we consume in the United States. Nuclear fusion is the antithesis to fission, in an atomic sense. American scientists began experimenting with fusion shortly after World War II, and produced what we now call a hydrogen bomb in 1952. The video you are watching here is a government recording of that first test. These thermonuclear weapons, which use the heat of a fission explosion to create a fusion reaction, are the basis for all subsequent nuclear weapon development. They are many, many times more powerful and deadly than the fission bombs dropped on Japan. Although fusion is much more powerful than fission, with a far greater energy release, scientists have been trying in vain for decades to unlock it as a source of commercial power. Now, what exactly is a nuclear reaction, and how does fission differ from fusion? The answer is actually fairly simple. Atomic science deals with splitting atoms into their three main parts: protons, neutrons, and electrons. The important thing to know here is that protons are positively charged and electrons are negatively charged. Think of this like you would a magnet. The positive end of one atom attracts the negative end of another, forming compounds. Also, just like a magnet, the positive and negative particles repel other particles of the same charge. With that understanding, here is the difference. A fission reaction is a violent breakup of an atom caused by bombarding it with neutrons. Continued input of particles creates more breakups, starting a chain reaction which unleashes a massive amount of energy, plus radioactivity. The animated diagram here helps visualize that process. A fusion reaction is the opposite. It is caused by forcing the negatively charged electrons from two separate atoms together. Normally, electrostatic forces keep these electrons apart, but when faced with a very high temperature, they can be forced into contact. This event produces a far greater release of energy than the fission reaction. All energy produced by our sun is created through a fusion process. Now that we understand the difference between these reactions, here are the implications for practical use, and I am not counting nuclear weapons as practical. All of the nuclear power generated on the planet today uses fission. The catalyst used in these reactors is most commonly U-235, which is an enriched isotope of uranium. Uranium is a semi-scarce resource that is highly radioactive. As you can see here, it has a half-life of millions of years. This means that spent nuclear waste, for all practical purposes, never goes away. Currently, we bury this waste in storage containers underground in remote parts of the country. Environmental issues aside, nuclear fission is a fairly cost-effective means of providing power. However, the supply is limited, and plants require extreme safeguards to prevent runaway chain reactions from causing meltdowns, which bombard the nearby areas with dangerous radiation. Despite these tight controls, there have been incidents over the years, including Russia's Chernobyl, 3 Mile Island in the United States, and Japan's Fukushima disaster 3 years ago. Power from fusion works a little differently. There are several generations of fuel that will power fusion reactors, each of which requires a higher technological achievement. The first generation will combine two isotopes of hydrogen, deuterium and tritium. Deuterium is a naturally occurring isotope found in seawater and is not radioactive at all. Tritium is more scarce and is radioactive. However, as you can see, with a half-life of 12 years compared to several million, it does not pose nearly the long-term effects that uranium does. The second generation of fusion will do away with tritium entirely, instead smashing two deuterium particles together. The other large benefit to fusion power is the nature of its reaction. Once a chain reaction has begun, it requires nearly perfect conditions to sustain. This means that any failure of equipment will result in a subsequent failure of the reaction within seconds. The nature of this process makes runaway reactions and meltdowns impossible. The biggest drawback to fusion power is, of course, we can't make it work yet. This slide is a quick glance at how the world currently receives its energy. As you can see here, the vast majority of it comes from burning fossil fuels. These are not sustainable and they are destroying ecosystems on the planet. We do have a small percentage of power coming from renewable sources like wind and solar, and a very small portion currently provided by nuclear fission plants. I just went over the advantages of fusion power a minute ago, but I will reiterate them here because this is the primary point of this topic. First, once we can achieve a second generation fuel, the plants will operate strictly on deuterium as the catalyst for their reactions. Because it is naturally occurring and found in seawater, there is enough supply to power the entire planet indefinitely, even accounting for increased energy consumption and rising population. In addition, the absence of radioactive material makes the plants extremely efficient and allows for repurposing of the land once individual locations are decommissioned. Finally, here are the big challenges facing fusion power. There are two primary ingredients needed, a sustained reaction and containment of that reaction. Getting the process started is referred to as ignition, and is akin to lighting the pilot light on your gas stove or water heater. Only in this case, the pilot light needs to achieve temperatures of 100 million degrees Celsius for several seconds for the first generation of deuterium-tritium, and 500 million degrees for the second generation deuterium-only alternative. Currently, we can ignite a fusion reaction with our nuclear weapons the quick and dirty way, start an explosive fission chain reaction in a way that it will set off a subsequent fusion blast. Detonating a nuclear weapon inside a power plant won't work to get controlled power started. Then, once that reaction has begun, it needs to be contained. There is currently no material on Earth that we know of that can contain this kind of blast. Therefore, most research has been looking at one of two ways to direct the reaction inward using either magnetic fields or lasers, which more or less forces the energy to travel around in a big circle. The research costs for this development are massive. Currently, the United States spends $250 million per year on fusion R&D, and even that isn't nearly enough to make reasonable headway. Combine that with the knowledge that once the power is available, it won't drastically reduce operational costs, and this has made it difficult to get additional funding. Right now, there are a few primary research facilities around the world. Notable is the Tokamak Fusion Test Reactor at Princeton University and an international experimental reactor in France, working with contributions from all over the European Union. These experimental reactors cannot generate either the sustained heat needed nor the containment required, but their repeated tests are moving the field ever closer to the end goal. The news that drew me to this topic for this presentation was a breakthrough that happened just this winter. For the first time, we have been able to create a fusion reaction that produced more energy than was required to make it. This may be a far cry from energy that we can use to power our homes, but it is a long-awaited breakthrough in the nuclear community, and one that is heralding progress towards their goal. Well, I hope this has been an interesting and informative presentation, and I look forward to hearing what some of you have to think about fusion power and its possibilities or drawbacks for our future. It has the potential to remedy our current energy crisis all on its own, but we may never make it there. I'm not an expert on nuclear physics, just an enthusiast who's followed news of its progress over the years, so I'm eager to see any knowledge or ideas anyone else has about it. Thank you for watching the video.